Dear MOOC learner, welcome to this new MOOC session that will focus on vaccination and pregnancy. We will go together through plenty of points, including why pregnancy is a great opportunity for vaccination, what are the immunological features of pregnancy, both for the mother and the fetus, some critical points for the design of a maternal vaccine, and finally, an overview of the current maternal vaccines landscape. Let's start by having a recap of what are the threats for a newborn. First, we have the developmental program of innate immunity that suggests an higher risk for suffering overwhelming infection with extracellular pathogens immediately after birth, and especially in the premature infant. You also have B cells that suggest higher risk for infection with extracellular bacteria for about 6 months, but for encapsulated bacteria for most of the first 2 years. Finally, change in the T cell number heighten risk over the first 2 years of life with intracellular bug linked to the dendritic cell ontogeny. But then, how a newborn can actually survive while facing all those potential killers? This is where the mother comes in front of the scene. The basic concept is that she will produce and pass to her children some antibody that will allow him to get some protection, while he is shaping his own immune system. Nevertheless, the protection conferred by those maternal antibodies is decreasing with time, and even with an immediate vaccination at birth, the newborn will remain with a window of vulnerability. If you have a low maternal antibody level at birth, this titer will quickly reach the threshold of non-protection. But if, on the contrary, the maternal antibody titer in the newborn is high, he will be fully protected against the desired pathogen during this former vulnerability window. The protection can even last more than the first months and provide a protection for encapsulated bacteria or intracellular bugs. Due to this sensitivity, children are exposed to many infections of any type, leading to an important global burden. Among the global cause of child death, 18% is due to the neonatal infections, resulting in 2013 in an overall of 625,000 deaths. As direct vaccination of those children doesn't fulfill our needs, vaccination during pregnancy represents a great opportunity for this infection. It's important to mention that other infections than those included here can be targeted, like pertussis. In fact, even if pertussis is still responsible for many child deaths, its burden has been drastically reduced thanks to a vaccination campaign for pregnant women. In addition to this, it is critical to mention that some threats also occur during the pregnancy itself. In fact, pregnancy period can be at risk both for the fetus and the mother. In fact, the maternal-fetal interface is a physical barrier to most extracellular microbes, a bit as a filter. But a mother can acquire some immune suppressive state with some intracellular pathogens like HIV, CMV, tuberculosis, varicella, or Lyme. You also have some pathogens specialized for a particular tissue. It has been shown that Listeria and malaria, for instance, had placental and fetal trimesm. Here is a recap of the different challenges. First, fetal infection can occur due to the constant communication and transfer from the mother to the fetus, like Toxoplasma gondii and Zika virus, among others. As those infections can occur at any moment of the pregnancy, the optimal timing for vaccination will be prior to pregnancy. Moreover, the pregnancy induces many changes in terms of hormones and on the microbiome that directly modulate the immune response of the pregnant woman, leading to an exposure to some pathogen like SARS, hepatitis E, or the now well-known Ebola. Some viruses can also target both the future newborn and the mother, like influenza. In this case, vaccination, both prior and during pregnancy, will be applicable. We will not enter directly in the detail of all those infections, but we will try to understand together how pregnancy can influence the immune response of the mother and the child, and why this is a great opportunity. Let's have a look now to the immunological components and specificity of pregnancy. The most remarkable feature of pregnancy is the capacity of the mother to tolerate the fetus, meaning her ability to accept this body in herself without considering it as a threat. To understand it, we have to remember that CD40 cells can basically differentiate into type 1 or type 17, leading to an inflammation, or type 2 and Treg, targeting tolerance. During pregnancy, the expectant mother's immune system undergoes various changes to tolerate the fetus. For example, extravirus trophoblasts secrete soluble HLA-G, producing IL-10, promoting then maternal tolerance. Prevention of immune rejection of the fetus results in the diminution of cytotoxic adaptive immunity and the enhancement of the regulatory adaptive response. The immunosuppressive molecule, like progesterone, prostaglandin E2, or anti-inflammatory cytokines produced during pregnancy also play a critical role. For instance, a high level of progesterone can alter the Th1-Th2 balance and inhibit the production of inflammatory cytokines. The maternal tolerance to the fetus has been considered also as a major factor to susceptibility to infection in pregnancy. Pregnant women are more severely affected by influenza, hepatitis E and malaria, for example, or preeclampsia that can break this new balance by promoting inflammation. However, the immune response for vaccine should not be impacted. Another key immunological component of the pregnant woman is her ability to potentially transfer antibody to child during pregnancy. But how is this occurring? This is thanks to the neonatal Fc receptor for IgG, FcRn, that bind the maternal IgG in an acidic environment and make what we call a transcytosis, going across the epithelial cell barrier and releases it at physiological pH. In rodents, FcRn is expressed on the cell surface brush border of enterocytes. Shortly after birth, rodents' pups ingest maternal milk containing IgG, which bind FcRn on the brush border in the acidic milieu of duodenum. Upon binding, FcRn transcytoses IgG and releases it at neutral pH on the neonatal side. In contrast to rodents, the bulk of maternal-fetal IgG transfer in humans occur antenatally across the syncytial trophoblast of the placenta. Those trophoblasts are bathed in maternal blood and internalize serum containing maternal IgG. FcRn is expressed in the internal vesicle of the trophoblast. On acidification in the endosome, FcRn binds to maternal IgG and transcytoses it to the fetal circulation where it is released at physical pH. This knowledge should then make us think twice before to consider data obtained from mice as true for women. Moreover, the transfer seems to occur during the whole pregnancy, but with an increasing rate. Then, most of the antibodies are transferred during the third trimester. More than species and timing frame, many other factors are influencing the antibody persistence. Obviously, it is influenced by the pathogen itself. For instance, antibodies transfer from the mother has been shown to be less persistent in the case of varicella, pertussis, and measles. Another parameter could be the region where the mother is living and her habits. Generally, newborns from developing countries have shown less durable persistence of the antibodies. This could be mainly due to malnutrition, but still remain unclear. After birth, the newborn can still receive some immunological component from the mother through milk. Those components can be dedicated to different purposes. First, it can be a protective factor that will help to maintain immune barrier function and will protect gastrointestinal epithelium by preventing colonization of pathogenic bacteria and dysbiosis of the microbiome. It provides direct and passive immunity to the infant, protecting him from microbial challenge. They also exert anti-inflammatory effect, promoting maturation, differentiation, and development of infants' gut-associated lymphoid tissue, the GOLD. Moreover, it promotes the development of tolerance to environmental and dietary antigens and of the microbiome. It's worth to mention that some factors can exert both functions. As we mentioned before, immunoglobulins are transferred systematically via the placenta from the mother to infant late in the third trimester, placing the preterm infant at an immunological disadvantage. Then, milk antibodies might be a solution. Secretory IgA is the most abundant antibody in human milk and provides critical antimicrobial defenses to the immature infant gut by preventing pathogens from attaching the mucosal surface. You can also find some IgG and IgM, but they are less abundant. It has been shown that secretory IgA concentration in human milk were inversely associated with risk of atopy in infant, but this only in conjunction with the other component we have seen before. To finish, it has been shown that maternal antibodies may interfere with infant vaccine response. The two essential immune mechanisms mediating the influence of maternal antibody and infant vaccine response are, in one end, that APC uptake of maternal antibody antigen complex, and in other hand, that there is some FCR independent mechanism. This led to the hypothesis of some epitope-specific masking and that there is some suppressive maternal antibody simply hiding antigenic epitope from infant cells. We can deduce from this that the lack of inhibition of infant T-cell response will impact the infant vaccines and significantly impact antibody response. Also, that the ratio of maternal antibody to vaccine against one antigen will be essential to determine the infant antibody response. This is represented here with the graph. Here we can see that if we have a maternal antibody excess, we will have B-cell antigen masking. If we have, on the other hand, antigen excess, we will have antigenic determinant free for infant B cells. This will lead to different situations. In the first example, inhibition of B-cell response, and the second hand, preservation of B-cell response. If we are at equivalence, we will have variable outcome, depending on the titers and of the epitope specificity. Just here, a small break to resume what is the point to investigate when developing a vaccine for pregnant women. You should look at, is the disease occurring during early onset of life? So is it targetable by vaccine during pregnancy? Is the vaccine dangerous for the regulatory immune-shaped mother and the infant? For instance, live vaccine are still not marketed yet. Third, is the maternal antibody transfer is occurring? So to investigate the FcRn receptor maybe. Are antibodies persistence, depending on the disease, of the geography? Is there an interference of maternal antibody with the current vaccine or with something else? And then don't forget that mice can lie. Now let's have a quick look at the history and to mention that maternal immunization passed during history from taboo to indication. In fact, before we were avoiding vaccination during pregnancy, while now the trend is to give mother and the unborn child the right on protection. The first example has been in 1879 with the successful use of vaccinia virus to protect infants from smallpox. We'll follow the wholesale pertussis vaccine, as well as in 1961 the maternal immunization with tetanus toxoid vaccine. Now let's have a look at the current landscape of maternal immunization and the schedule. First, for women planning a pregnancy. Those women should be vaccinated before pregnancy according to the adult immunization schedule. Several infections with serious consequences can be prevented by preconception vaccination. For example, MMR vaccine. In fact, rubella infection during pregnancy can cause severe birth defects. Varicella vaccine also has primary varicella infection during the first 2 trimesters can cause congenital varicella syndrome. Then we can vaccinate during pregnancy. And here it is always nice to recall that there is no evidence of harm to pregnant women or fetuses from the administration of inactivated vaccine. Then tetanus, diphtheria, and influenza are routinely recommended for all pregnant women. In fact, tetanus is a life-threatening bacterial disease, and if a pregnant woman has not previously been vaccinated or her immunization state is unknown, she is advised to take 2 doses of vaccines 1 month apart before delivery. Concerning flu vaccine, it can be given during any trimester of pregnancy. Finally, you also have vaccination after pregnancy. Following delivery, women should receive all the recommended vaccines that could not be or were not administered during pregnancy, like MMR or varicella, to protect themselves and then prevent transmission to their babies. Both inactivated and live vaccines may be administered. Breastfeeding is not a contraindication to administration of these vaccines. Here is a complete list of vaccines and their use. Some vaccines that were not mentioned previously and of great importance are here, like meningococcal or pneumococcal vaccine. What could be the future maternal vaccine to develop? It is globally accepted that the main priority should be RSV, the respiratory syncytial virus that causes viral lower respiratory tract. If it's in general well treated, many deaths still occur. Researchers are struggling with it for a long time now, but some promising vaccines are currently in phase 3. Here is what's it to mention that one previous clinical trial using the post-fusion state of the F protein had led to an enhancement of the disease and to child death, speeding down the global effort for an RSV vaccine. The second opportunity could be GBS, the leading cause of pneumonia and meningitis in children. Finally, the risk of neonatal herpes and congenital cytomegalovirus infection is really high in women with primary infection during pregnancy. To finish this presentation, some key points that can drive the implementation of vaccine. The main priority is of course that this vaccine must be safe, as always. Next, it is important to mention that authorities are now asking for a specific clinical trial evaluating the safety and efficacy of the vaccine in pregnant women, which was not the case before. Thirdly, it's important to take into consideration that each country can adapt the vaccine recommendation from WHO. This can explain the huge diversity of schedule depending on the country. This is now the end of this presentation. I hope that you appreciated it and that you are now more aware of key parameters to consider when dealing with maternal vaccination. Thank you.